Namaskar, welcome back. So, in last lecture, we were talking about the antithetic and synthetic faults. Now, let's see about the rupture part. So, surface rupture, and this will remain mostly common for other environments also. So, what we mostly see is that the sense and amount of displacement varies along the strike. So, if you see the orientation, and suppose you are having an east west strike. Okay. So, amount of variation will not be the displacement, amount of displacement will not be the same and will be maximum where you are having the maximum energy has been released. That is what we call your epicenter part. So, suppose you have then the central portion where the maximum energy has been released, that will have the higher amount of displacement. So, vertical scarps, if we see mostly in because it is 50 to 70 degrees and all that. So, at the base you will see the material which has been eroded. So, this is an eroded material which has fallen down from this scarp actually. But as I told that this depends upon the lithology. The scarp will degrade faster if you are having very loose material, but if you are having indurated material, and that what we were looking at one of the photograph of the scarp which was 3 point something meters, okay, and which remained very intact, and then the photograph B also shows that if you are having intact material slightly indurated or it is cemented, then you will see a scarp which is standing as it is, okay, with fewer material which is or lesser material getting eroded and deposited at the base. Okay. So, pattern of rupture also depends on the nature of material. Normal faulting usually has been seen around 50 to 70 degrees. Threshold of surface rupture is like 5.5 to 6.5 magnitude. If you are having this magnitude, then you may expect a rupture in that area. Okay. In US, it has been observed that most of the earthquakes with magnitude greater than 7 will result into the rupture. Again, the rupture is dependent on your material which has been seen. Okay. Then coming to the stratigraphic evidence of paleo earthquakes in normal faulting environment. So, tectonic versus depositional features. So, as we have started in the when we started in the beginning and we talked about the tectonic and non-tectonic structures, okay, in terms of the sedimentary structures. So, here also we will try to see that part, okay, similar one. So, difficult for the geologist to identify faults in soft sediments, whereas easy in hard, because it will in hard rocks you will see a very clear cut scarp. Okay. Normal fault usually accompany with development of fissures and fissures filled with rubles. Okay. So, after the extension is there, then you will see a sort of an infilling of the fissure. So, when we open up the section, okay, try to see the section, then you will be able to identify these features also. Okay. And this could be because along the antithetic and synthetic faults which are not deep rooted, which are superficial. Okay. But in case of strike slip faulting, one can see polished slicken sides. Okay. So, if you are having, for example, in strike slip, if you have a movement, for example, a left lateral movement, so if this block has moved away and this block is moving towards us, then we call this as an left lateral movement. Now, in case of the left lateral movement, if the movement is almost horizontal, it's not having any oblique displacement, then on this you will see sort of striations, and that is what we call slicken sides. Okay. So, these are been termed as slicken sides, provided you have exposed section, and brecciated contact along the fault plane in case of reverse and thrust fault. So, this part we have already discussed when we were talking about the shear fabric. Now, difference between the fault contact and the erosional or depositional contact, you see the fault contact in unconsolidated sediments have steeper depth, no primary structures can be seen, only the shear fabric, and this remains same for the reverse faulting also. Okay. That is what we discussed in one of the previous lectures. Okay. So, we have very preferred orientation of elongated clast we will see along the fault plane, and fault contacts are straight and become steeper upward at the surface or gentler. Now, in case of the depositional contacts or erosional contact in unconsolidated sediments are usually gentle, and those are like the cross stratification and troughs of the or the bonding surfaces which have been seen. For example, you have something like this. Okay. So, you have a contact here, okay, but these are all depositional contacts. So, they will be much more gentler as compared to your fault contacts. Primary structures are present. So, depositional structures will be there, erosional structures will be there, and this we are talking about the sedimentary structures. Okay. Few clasts show preferred orientation, whereas in the faulting fault contacts you will see a very preferred orientation of elongated clast. Okay. Contacts are not straight, concave upward. So, this part we have if you see, I think we have discussed this, but if not, then we will quickly look at this. Okay. So, this is an example from a paleo channel here, which you can see this one, this part. You have a paleo channel, and of course, this having in contact with the previously deposited material, which are horizontally stratified. Okay. So, if you come across this part only and then see this one, you may uh, like infer that this is in fault. Okay. But then close view of this portion has to be seen, whether we are having oriented clast in this or not. Then is there any sort of a deformation we are able to see in this area or not? That those things have to be taken into consideration to nullify that this, or to infer that this is tectonic or non-tectonic contact. Okay. But this is a non-tectonic contact, what you see here. Another one in case of the gravitational slides also. So, distinguishing between tectonic and non-tectonic, that is depositional features, example due to slumping, okay, and that is what we call gravity faulting. So, we will have a very typical curved contact, okay. It will not be very straight, okay. This type of faults are curved and have concave up geometry. So, this is your erosional contact. This part also we have discussed in one of the lectures. So, where you see a displacement, clear cut displacement along this line. Okay. So, these are not a depositional or erosional contacts. Okay. These are faulting because you can make out easily the respective displacement in terms of the layers. Again, this is your the deposition of the channel fill, but this is not. Okay. So, this contact is tectonic contact, and this one is your, we can say, a depositional, or the contact will be like erosive contact over here. Okay. And you have even the primary structures which have been seen here, the typical cross stratification. This is your erosional, or we can say non-tectonic contact. But this one which goes right up to the top is your typical reverse faulting contact. Now, normal scarps, if we look at, then as I have mentioned in the previous lecture, that we need to understand the overall process, okay, because once the scarp has been formed, there won't be immediate displacement observed by that fault. Okay. It will take time, and that will be because it will accumulate the strain, accumulate the energy, and finally then again it will release the energy. So, between that period, that is what we call interseismic period, the erosion will be the scarp will be subjected to erosion, exposed to environment and all that. Okay. So, you have rain, you have other processes also that will degrade the scarp. So, for example, if you say that, okay, fine, this was the scarp which was formed earlier, for example, if you see in the section, okay. So, this is in case of the reverse fault, okay. But in case of the normal fault, then you have sort of this portion is going down, for example, and then you have this block has moved down. So, this is in the normal faulting environment, and this is in the reverse faulting environment. So, over the time what is going to happen is that in case of the reverse fault, this will degrade, okay. And then final what we will see is this topography. Okay. So, earlier it was like this. So, this portion is eroded, erosion. Similarly, over here in this case you will see sort of this topographic profile. So, this portion will get eroded. Now, one thing which I would suggest you to keep in mind, in both the cases, if you see the topography, then you have this topography after erosion, and in the this is in the that is in the reverse, and this is in the normal case. Okay. So, in both the cases you see the topography something like that. So, in reverse case the fault is like this, okay, which is moving up, this block is moving up, and in the reverse normal case the fault was like this, okay. The fault is here. So, in this case the fault is here actually, okay, which has this block has moved down. So, in both the cases the topographic expressions remains the same. Okay. Let us move further. So, you have the down faulting which has been shown here. So, this two were the surface which were together, and there is a movement along the fault here. Okay. So, this is the original surface we are having, okay, which were together before, and then we have the degraded scarp. Okay. So, that what we call as a free face, and this one is your debris slope, where the material is eroded and getting deposited. Okay. Then finally, this is wash slope. So, in debris flow area, you will have comparatively coarser material, and wash slope you will have finer deposits. And this is the toe. This is very much similar to what we see mostly in the landslide areas, okay, or landslided material. Now, degradation of the scarp is again dependent on, one is the material, and second is your the angle, okay, at which it stands. Okay. So, fault scarp degradation, for example, you are having if you come across multiple scarps in normal faulting environment we are looking at. Okay. And here again you what you see is a very typical, sometimes you will see a very clear triangular facets here. Okay. And at the base of this what you have is you have the scarp, okay, which goes over here also. Okay. So, this is your scarp which has been seen. Okay. And then you, if you have the scarp above, then you can, that what we were talking about, that we can say that there are multiple events which have occurred here. So, after faulting, scarp are exposed to weathering and erosional process. Okay. So, degradation of the scarp in unconsolidated sediments usually depends on the angle of repose. Okay. That is the angle of the free face, okay, which we are talking about in the previous slide. Okay. So, what we have is now that again the scarp angle, okay, is important, that is what we call the angle of repose. So, the after the formation of the scarp angle is higher, but it will start eroding from the free face and start depositing in medial part and as well as the wash face as the toe of the scarp. Okay. So, this dotted line is showing your erosion which is going on, okay, and this portion will be deposition, this will be eroded. So, 30 to 35 degrees for unconsolidated sediments, okay, and that is your free face what we are talking. Okay. So, after erosion it will stabilize somewhere there, okay, but for 30 to 35 is for unconsolidated sediments and 60 to 90 degree for the massive hard rock. That means that if you are having softer material, then you may expect a sort of an scarp like this after degradation, but if you are having harder one, then it may stand as it is. Okay. That is up to 60 to 90 degrees. So, degradation continues as shown in C, and this profile will start smoothing up actually the topography of the scarp and during the degradation process. Okay. And finally, it will stabilize. Okay. So, slope stabilization will occur at around 35 degrees, okay, in case of the loose sediments, and further it goes up to like as gentler as 8 to 25 degrees. What we are interested further, of course, this slope, the stabilization of the scarp slope and all that, but at the same time the wash slope area or debris floor areas. Okay. That is those are also important when we are talking about the paleoseismic events and all that, because the deposition will be here in this area, and that what will result into the your debris, deposition of debris here, and this part will be erosion. So, the portion which has been eroded and deposited at the toe of this exposed scarp, that will result into what we call is, because they are mixed up material and they are not well sorted. So, we call that as an debris material and colluvial wedges. Okay. So, scientists have worked on this colluvial deposits in the trenches. I'll just explain that part over here. So, suppose you are having this initial scarp formation, and then you have the erosion and deposition over here. So, this will be your colluvial wedge. Okay. So, if you are having the deposition over here, okay, then whenever there is an earthquake, this already we have discussed in the one of the lecture, that whenever there is a next earthquake, this colluvial wedge will be displaced, and again you will have the formation of colluvial wedge in this area. So, multiple colluvial wedge can also help us in identifying the events. Okay. So, it is a concept of model utilized for deciphering faulting history. So, you can go back into the history and say that okay, how many colluvial wedges are there, that can help you. Okay. So, by identifying the colluvial material deposited at the base of the scarp. So, this is the base of the scarp. Okay. So, this one is your base of the scarp here, this part. Okay. So, this part will be accumulating your eroded material, and that is what we classify as an colluvial material. Again, coming to that photograph here, what we see at the base is here is the colluvial material. Of course, this is this portion of the scarp is comparatively hard as and that is one of the reason that it has still showing very sharp appearance. Okay. But at the base you have this one is colluvial wedge, or you can say colluvial material. Now, in trench, so before I go to this, so mostly when we like open up the section, this also we have discussed. So, we will try to cross this. Okay. And of course, the fault is sitting somewhere here. So, we will see the colluvial wedges. Okay. So, in trenches, because when if we, wherever you are having this scarp here like this, so you mostly what we do is that we will open up this part here. So, this will be the excavation of the. So, there is a trench in which we see the try to see the signatures of paleo earthquakes. So, people have tried to see this in trenches where they have identified like this is colluvial wedge 1, this is colluvial wedge 2, and fault is sitting somewhere over here. Okay. Now, in this case, of course, we can easily say that there were 2 events. Okay. Because we have 2 colluvial wedges. Okay. Now, for example, here we have again the colluvial wedge. This is from a thrust, or we can say this is an oblique faulting environment. Okay. Where we have the movement is something like this. Okay. So, this portion is going up and this is sliding down. So, this I would say, but this is in the overall if we take this is in thrust faulting environment, but this component is something like this. Okay, which has gone down here. So, this could be we can say that this is a normal faulting environment and fault is somewhere over here. Okay. And we have multiple colluvial wedges here, one is sitting here, another one is when seen this one. Okay. So, at least 2 events we can demarcate in this area. Okay. Anyway, coming to further this the free phase and all that we have already discussed, and how the overall slope stability will take place, and then the erosion stops. Okay. So, faces model also debris faces poorly sorted, because the material is not traveling a very large distance from here. Okay. It is just sliding down and then falling in at the base. Okay. So, if we classify that, then debris faces are poorly sorted, then poorly stratified also, because they are not getting that short of a long distance to get properly deposited. Coarse grained, okay, it will be larger class of intact soil. Okay. Because they are falling from the faulted surface. So, they will be like intact, and they will mismatch the overall, like the structures, internal structures will mismatch the overall structures we see in the trench exposed. Okay. So, you have little or no matrix in that sense. Okay. Then further, continue to deposit until the free phase disappears. That is the process of the stabilizations which we are having. Okay. Then wash phases, if you go at the towards the toe part, then they are well sorted because they are getting further like deposited in the some distance they travel, but they will not be coarser one. Okay, they will be mostly well stratified and finer ones. So finer one will have easy sort of an process to get deposited and stratified. Okay, so they are fine grained. Okay. So this we are talking about the scarp here. So this will be the portion of the debris, and this will be the portion of the wash phase. Okay. So wash phases, and this will be your debris phases. I've made little high angle, but yes, you can talk about this. Okay. So deposition starts after the disappearance of the free phase. Okay. And then finally, if you see, then mainly by the process is slope wash, rain splash, or creeping. Okay. So with this, we'll stop here. We'll continue with this part in the next lecture, where we will talk about the multiple your debris, or we can say the colluvial material, how we identify the multiple events, okay, or more than one events based on that. Till then, thank you so much. Namaskar.